Okay, everybody. So just to give you a little bit of chapter 6, matrices and determinants, matrix solutions to linear systems. So this is designed to show you what the point of systems of equations is, right? Because it's connected to, and when I say connected, I mean directly connected to a lot of advanced mathematics. Okay? So the objectives are writing an augmented matrix for a linear system, performing matrix row operations, using matrices and the Gaussian elimination to solve systems, and then using matrices and the Gauss-Jordan elimination to solve systems. So this is what matrices are used to display information and to solve linear systems. A matrix, plural, matrices, is a rectangular array. Matrices are used to display information and solve systems, linear systems. And a matrix, in the plural form of matrix, is matrices, is a rectangular array. So it kind of looks like a table in a sense. The information is arranged in rows and columns, kind of like how a spreadsheet looks like in a table. And the values inside the brackets are called elements of the matrix. So there's an example, and the arrows are pointing to those. It does not always mean that there are numbers inside the matrix. The first step in solving a system of linear equations using matrices is to write the augmented matrix. An augmented matrix has a vertical bar separating the columns of the matrix into two groups, and the coefficients of each variable are, so if you imagine 2x, the coefficient, which is 2, will be placed in the matrix, and it will be left to the vertical line. And when they say and the constants are placed to the right, those are what is after the equal sign. If any variable is missing, you need to place a 0 in for that variable. So you can pause the video and take notes and then look and see what this looks like. So if you notice, you have a 3 here. So the 3 goes here. And if you don't have a number in front of a variable, then it's a 1 inside the matrix. And then you see here's the equal sign, and then there's that bar. So writing an augmented matrix, just imagine what you would put inside of it. Replace any missing variables with zeros, and there you go. And remember, you can always pause the video if you need to. Matrix row operations. So there's many different ways that you can maneuver items inside the matrix, but you do have to stick with row operations in terms of how you move them around, what you add and subtract, and where you place things. So a matrix with ones shown on the main diagonal and zeros below the ones is said to be a row in row echelon form. We use row operations on the augmented matrix to produce a matrix in row echelon form. So just notice where those zeros are and where the diagonal of ones are. The following row operations produce matrices that represent systems with the same solution set. 2 rows of a matrix may be interchanged. This is the same as interchanging 2 equations in a linear system. The elements in any row may be multiplied by any non-zero number, and that just means by multiplying by a number so that you can manipulate it to get those ones on a diagonal, and then you just possibly add or subtract. You can even multiply by fractions. The elements in any row may be multiplied by, again, a non-zero number just means a number. It could be a negative number. Does not always have to be a positive number. The elements in any row may be multiplied by a non-zero number. That, again, just means that it's a number. It could be negative, it could be positive. And then these products may be added to the corresponding elements in any other row. This is the same as multiplying both sides of the equation by a non-zero number and then adding equations to eliminate a variable. Two matrices are row equivalent if one can be obtained from the other by a sequence of row operations. Each matrix row operation in the preceding list can be expressed symbolically as follows. So they're using I and jth rows. So that just means it's one particular row and another particular row, like kind of how you label your equations, equation number 1, equation number 2. We're saying, this could be row 2, and it goes to row 3 or something. So you can interchange those rows. You can multiply each element in the ith row by a scalar or a number. You can add k times the elements in the row I to the corresponding elements in row j. So this is saying I can multiply a number to row I and then add it to row j. But normally we say where it's going to go. So normally we have an arrow and we say, and I'm just making this up, it could go to row j. So perform the indicated row operations. So this means we're just going to switch row 1 and row 2. And it is a good idea to label row 1, row 2, row 3. That way you can keep track. I know when I first learned row operations, I was so confused because I didn't understand the terminology. I didn't understand that this was saying to me that I could go, that I'm switching the rows. That's really what it's saying. So you see here, row 1 goes to row 2, and row 2 goes to row 1, so it's a double-sided arrow. So you're just switching the rows. In this one, we're just multiplying 1/4 to row 1. And you have to multiply it to everything in row 1, so be careful about that. I've made those kinds of mistakes in the past. And then the rest you just copy. The rest of the rows you just copy. And then for this one, we're multiplying 3 to row 2, adding it to row 3. Normally, we do not do it this way where we put the entire thing inside the matrix. This is a lot of writing across a matrix. So normally, we would just multiply 3 to row 2, right? And we would just get that, and then we would add it. So what do I mean by that? So we would take 3, we have 18, and then we have 9, right? And then we get 21, and then we just add it to row 3. So we just copy that, and -9, and that you can even put the little bar there so you know. And then we get 0, 16, 10, as long as I did my math right. And I believe, what is that? 12? You can even put that there. Oh, did I make a mistake? Where did I make a mistake? If I multiply. Oh, it's -9. That's where I made the mistake. Haha. And I do not know where my eraser is. Oops. So we're just going to cross that out and write -8. So there you go. So you see how you can make a simple mistake. But I caught it. Okay. Now, solving linear systems using the Gaussian elimination method, solving linear systems of 3 equations with 3 variables using Gaussian elimination. So we write the augmented matrix, and then we use row operations. We want to get 1s on the main diagonal from the upper left to the lower right, and then zeros below the ones. So this one here. Write the system of linear equations corresponding to the matrix in step 2 and use back substitution. So this is now we're moving into the place where we are showing you how to solve a system of equations. Solving systems with 3 variables is difficult, so you write the matrix, right? And then we start to do, and you can pause the video, remember. So we start to do operations that will give us ones on the diagonal. So we swap these 2 rows. We almost have all the ones on the diagonal. Use row operations. So -2. And this is the decision that you have to make. But in this PowerPoint, they're showing you what to do. So -2 times row 1 plus row 2. And we are replacing row 2 by that. Normally, it just says go to row 2. Okay. So you perform that and then replace row 3 by -1 times our row. It says R1, but it's row 1 plus row 3, and it goes to, it goes to row 3. And then use the same method, switching row 2. Switching row 2 and row 3. And then that's, again, a decision that you want to make because you see what you can do. Multiply row 2 by 1/3, which is going to give you a 1 in the second row in the middle. And then you replace that row. And then replace row 3 by multiplying a -3 times row 2 and adding it to row 3. And that's how you get your diagonals and your zeros. So your ones in a diagonal and your zeros underneath. And then you can solve. It's like you have one variable that you know to be true, and that's z, right? So z equals 3. So you can substitute z in for the second equation, and then you solve for y. And then you can take the first equation, plug in z and y, and you can figure out what x is. Okay? So that's how you get warmed up to row operations and swapping rows. And by the way, the Nspire calculator does amazing things with this. You can actually do it step by step in that calculator. I think the 84 does some stuff, but I'm more versed. I know more in the I know how to do it better in the Nspire. So, solving linear systems using the Gauss-Jordan elimination method. So, write the matrix as before. This is pretty much the same. Pretty much the same. Get 1 in the third row, third column. Continue this procedure as far as possible. And then use the reduced row echelon form to back substitute. So that is what we just did. Okay, so we already have our solution, right? But we can continue and then solve just using the matrix instead of back substituting. So we want zeros in those open positions. We want just ones on the diagonal. So we replace row 1 by adding row 2 and row 1. Now we have a 0 there in the second column. Then we can replace row 1 by multiplying -1 to row 3, right? We're adding it to row 1, but we're going to place it in row 1. Now we have zeros in the first row, second and third column. So now we know that x is equal to 5. We also know that z is equal to 3. We're sure of that. So this one and this one we know. So we still have to manipulate the matrix to figure out what y is equal to. So replace row 2 by adding row 3 and row 2. And there you go. This is your x, this is your y, and this is your z. I know that's not lined up perfectly, but there you go. So we just used the same problem and we figured it out just using the matrix. Next, I'll move on to 6.2. All right, so for the next section, we're talking about inconsistent and dependent systems and applications. So I'm going to go through this probably really fast because inconsistent and dependent systems, I can't tell you that they're very, very useful. So the objectives here: apply Gaussian elimination to systems without unique solutions. Apply the same thing with systems that have with more variables than equations, and then solving problems involving systems without unique solutions. So inconsistent and dependent systems, if you think about it, what did they look like actually when they were in a system, right? So with x and y, or maybe z, right? So in the case of systems with no solutions, or dependent systems with infinitely many solutions, it is possible to rewrite the augmented matrix in the desired form with ones down the main diagonal from upper left to lower right and zeros below the ones. So a system with no solutions. When you first look at it, you really can't tell. Okay. So you write your matrix, and then you can attempt to simplify, and you can pause the video if you want to slow it down and go along with the row operations. And you see that you have your third row has no z. So it says here that, this is not true. You have no 1 on the diagonal in the third row, so has an empty set. The solution is the empty set. And then here, start with an augmented matrix. Remember, you can pause the video. And if you look in the matrix on the right, they're exactly the same. Row 2 and row 3 are exactly the same. That's a little bit of an indication that something is not going to be unique. This equation results in a true statement regardless of which values are selected for x, y, and z. The equation is dependent on the other two equations. So you would write the solution as two other equations. So you could just have z, and then you solve for the other two equations in terms of z. Now, here you have 3 columns, but you only have 2 rows. So you see here, they solve for x, they solve for y, everything's in terms of z. Okay, so just one more thing. There is a matrix calculator with Desmos, so you could just Google it. And I just want to show you how you make a matrix. So I'm going to start with a 2 by 2. So you see here, you can choose to make more rows or make more columns. And then I'm just going to put the numbers 1, and you can hit the tab button on your keypad on your computer or keyboard, 2, and it takes you to the next one, 3 and 4. And I'm going to go ahead and hit enter, and then I'm going to create a new matrix B. And when you hit new matrix, it just happens automatically. And I'm just going to do it backwards, so 4, 3, 2, 1. And I can do matrix A plus matrix B, and it gives me my result. Isn't that cool? So